Okay, good afternoon. Any questions, comments, anything you want to ask? Okay, we'll work on sinusoidal time dependence today. We already looked at a perturbation which had some amount of sinusoidal perturbation in it, but this is an important topic because that's how we usually excite particles from one energy to another, and therefore we have to look at what happens when we have some sinusoidal time dependence. Now, we will, let me just put down a form of the perturbing Hamiltonian. Suppose I have a perturbing Hamiltonian which has the form some V over R and then cosine omega t, okay, something like this. In fact, last time I called this the capital omega, so let me be consistent. Okay, so I have something like this, which is acting on the system. Now, remember that we had these equations, which we wrote down as Ca dot is equal to 1 over h bar, and then I had the matrix element of this object. So the matrix element, so this means that if I look at the matrix element of this h prime between two states, okay, I'm going to get something which looks like VAB, and then the time dependence will still be there. Okay, so I'm going to get something like that. Okay, so this is going to give me VAB, and we had this e to the minus I omega 0 t. What was omega 0? We are looking at this two-level system. There's an EA and an EB. EA we took at as lower energy, and then we had this h bar omega 0 energy difference between the two states, and then I had this CB here. Okay, obviously I also need the cosine omega t. Okay, CB. Okay, so I have something like this. And then last time we said, okay, let's just expand this so that we have Ca dot is equal to 1 over I h bar VAB e to the minus I omega 0 t, and I have 1 over 2 e to the I omega t plus e to the minus I omega t from the cosine, and CB. Okay, then he said, okay, we are going to be looking at, yes.
Can you remind what was CA and CB?
Okay, what are CA and CB? Okay, CA and CB are the wave functions. Okay, so let me squeeze it someplace. Let me put it over here. So Ca, the wave function that I have, psi of t is Ca of t e to the minus I Ea t over h bar plus Cb t e to the minus I Eb t over h bar. Okay, so psi, I am in this two-dimensional Hilbert space now. Okay, I have this just UA and UB, which I should include there. Okay, so sorry about that. So there's also a UA of t and CB of t e to the minus I EB t over h bar UB of t. Okay, so I have a linear combination of these are x or r, whatever in general. Okay, so these things are the eigenstates of the unperturbed Hamiltonian. So I have H0 UA is equal to EA UA, and H0 UB is equal to EB times UB. Okay, so I have these two eigenstates, and I am assuming that there's nothing else. Okay, and I can always express any function in terms of a linear combination of those things. Now, if there's no h prime, remember, then these things are just constants. Okay, that's what we did throughout the first semester. We expanded any function in terms of the eigenstates and just introduced these stuff. Okay, so if there is some h prime, which is weak in some sense, that will induce a change in these coefficients. Okay, so this will result in a change in CA and change in CB, and that's the equation which is describing that. Okay, so that's what we had for how this CA was changing, and we said, okay, this is going to, the terms that are going to be contributing are going to be terms that are changing slowly. Okay, and therefore these things, when they add up, omega 0 plus capital omega, it's going to be a higher frequency and will contribute less. So we said, okay, let's throw that away. Okay, and we just looked at the term which had this omega 0 minus omega term. Similarly, I'm going to get a CB dot equation, which is 1 over I h bar VBA this time, e to the plus I omega 0 t, and then the cosine function again, which is e to the I omega t, okay, plus e to the minus I omega t, okay, CA. So in this case, the argument says, okay, this omega 0 and omega are going to add, so they are going to make up a big omega, large omega, which is going to oscillate very fast. But there are places where omega 0, when it's near capital omega, is going to be small. So oscillations will be small and contributions are going to be larger. So in that case, okay, we throw away this term so that we are left with omega 0 minus omega. Okay, so that's what we did when we were solving it. Now, after that, we constructed the perturbation theory, right? We got the first order, second order terms, etc. Now, when you throw away these terms, okay, a very smart person, a rabbi who was a pioneer in spectroscopy of atoms, he noticed that if you just throw these things away in your perturbation theory, well, if you are going to neglect these things, then you can just consider these equations from the start, and then you can solve these things analytically. Okay, you don't have to do perturbation theory if you throw those things away. Okay, so this cancellation, okay, so cancellation of these terms is called the rotating wave approximation for historical reasons, okay, which does not have much, in our problem, it doesn't have much relevance to a rotating wave, but that's what it's called. Okay, so, and abbreviated RWA. So within the RWA approximation, these are your equations, and you can solve them, okay, analytically without doing perturbation theory. So that's an important thing because, first of all, because it takes care of the sinusoidal time dependence problem. Okay, we get a solution for it. And not only that, but we can also look at the accuracy of the perturbation theory. We can see whether the perturbation theory is accurate, working all right. Okay, so let's look at that. Let's look at the rotating wave approximation. So I want to solve these equations within this approximation. You see I have derivative of CA related to CB. Derivative of CB is related to CA. And typically what you would like to do for problems like this, okay, something which usually works, is to combine the two equations for a single variable. Okay, so try to get an equation for CA. Obviously, these are first order time derivatives. So it's going to, if you just remove one of the variables, it's going to be a second degree equation, right? So let's, in fact, do that. Let's look at this equation, okay? And let's look at its time derivative. What do I get for CA double dot? Okay, so if I differentiate it one more time, you see there are factors of t here and there, but I'm also going to get a CB dot. Okay, and CB dot then is related to CA. So what I'm trying to do is I'm trying to eliminate CB from the equation. Okay, so what does that give me? 1 over I h bar VAB, and then there's a factor 1/2 now because of the cosine. And I have an e to the I omega minus omega 0 t, right? So it's going to bring down an I omega minus omega 0, okay, from the exponential. And I'll still have e to the I omega minus omega 0 t, okay, those two terms combined, times CB. But I'll also have a derivative of the CB. So there is going to be a second term plus 1 over I h bar VAB.
We also have 1 over 2 IH bar.
Yes, we again have the 1 over 2, thank you. Okay, VAB. And then I again have e to the I omega minus omega 0 t times CB dot. Okay, so for CB dot, I'm going to insert the second equation. But I also have a CB here, which I do not want.
So you'll insert the first one.
Yes, so I'll insert the first one. So what I'm going to do is I'm going to look at this equation. That equation says that, okay, certain part of that term, so CA dot is equal to 1 over I h bar VAB. Okay, 2 is still there. And e to the I omega minus omega 0 t, okay, CB, right? So that's just the first equation. I rewrote it. You see that's already here. I h bar VAB. This part is not there, but the rest of it is still there, right? Okay, so that piece there, which is going, just tells me that it's equal to I omega minus omega 0 times CA dot. Okay, so I just replace that part of the equation, which is the whole term except this one, is equal to CA dot. And then I have 1 over plus 1 over 2I h bar VAB e to the I omega minus omega 0 t times CB dot, which is 1 over I h bar, okay, another factor of 2, and then e to the I, this time omega 0, this t is there, omega 0 minus omega t times Ca, right? So, okay, the exponentials cancel. And I have a equation for Ca.
Because we have upper omega minus omega 0 and omega 0 minus upper omega, so they are not the same.
What do you mean? I omega minus I omega t minus omega 0 plus omega 0.
Yes, so how do they cancel? They can cosine.
No, they are being multiplied.
Oh, okay, I'm sorry.
Okay, they are being multiplied, so I just add up the exponents, okay? All right, so this then tells me that Ca dot dot is equal to I omega minus omega 0, Ca dot, and then I have some stuff. Okay, did I put everything in here? I didn't. I forgot to VBA. Right, anything else? Okay, seems to be okay. Okay, so this term here is going to be minus 1 over 4 h bar squared. VAB times VBA is magnitude of VAB squared, right? Because they are complex conjugates. V is a Hermitian object times Ca. Okay, so that's the equation I have to solve. Doesn't look terribly complicated. So what do? We assume a solution, okay, which of the form Ca is equal to some constant times e to the I. I'm running out of omegas. Okay, so omega t. Okay, so let's just make that a plain omega. And put that in. So obviously, I can always multiply this by a constant, etc. It's a second degree equation, so most likely we are going to get 2 solutions, okay? And the general solution will be a linear combination of them. Okay, so second derivative of Ca, okay, is going to be minus omega squared times e to the I omega t is equal to I omega minus omega 0 I omega times e to the I omega t, and finally minus VAB squared 4 h bar squared e to the I omega t. So e to the I omega t is cancelled. And I'm left with an algebraic equation which I need to solve. Okay, so it's omega squared plus whatever. Let me write it one more time. So omega squared minus omega minus omega 0 small omega minus VAB squared over 4 h bar squared is 0. Okay, so omega must satisfy this equation. So let's see what we get. Okay, so I'm going to get 2 solutions for omega. Okay, so minus v, okay, 1 over 2. So it's going to be 1 over 2 omega minus omega 0 plus or minus 1 over 2 again. Okay, b squared, which is omega minus omega 0 squared minus 4, okay, so that takes care of that, for VAB squared or h bar squared, right? Minus 4h, so it's going to be plus 1/2. Okay, so I have two frequencies, omega 1 and omega 2, okay, depending on whether I have a plus sign or a minus sign there. And so let's give this a name. Okay, so this is 1/2 omega minus omega 0. This piece at the square root is called yet another omega, omega Rabbi, after the first guy who solved this problem. Okay, so now I have those things. So my general solution is in the form C A is going to be some A e to the I omega 1 t plus B e to the I omega 2 t, right? Okay, and CB, okay, is not independent, so I can find what that is. Okay, so it's down here where you cannot see, but that's an equation which says, okay, so the first equation there says that CB is equal to, I'm going to get a CA dot divided by that term, okay, and that term is 1/I h bar VAB, okay, e to the I, which way does it go? Omega minus omega 0 t, and there's a factor 2. Okay, I have just copied the time-dependent equation order. Okay, so I guess that's that. So you can just put it in there. Okay, so CA dot is I omega 1 e to the I omega 1 t plus I omega 2 e to the I omega 2 t divided by all of this 1/2I h bar VAB e to the I omega minus omega 0 t. Okay?
Why did
Yes.
you omit A and B constants?
Why did I omit why I? Okay. So whenever you have a question which says why, most likely I made a mistake. Okay? So A and B are there, obviously. Okay, so that's the general solution. But let's look at a certain particular initial condition. Okay, so as an initial condition, suppose at time equal to 0, I have this A, which is the, well, it's CA. I want it to be equal to 1, which means that the particle is definitely in the A state, and CB is equal to 0. Okay? So that means, okay, let's just put time equal to, so these initial conditions imply, if I put time equal to 0, I am going to get A plus B is equal to 1. And then this object, which says time equal to 0, so I times A omega 1, right? the exponentials become 1s, plus b omega 2 is equal to 0. Okay, I don't care about the factor.
Hocam, there is also a denominator.
Yeah, but it's equal to 0. Okay. So this then tells me that, for example, b is equal to minus a omega 1 over omega 2. And if I put that in here, then I'm going to get, okay, from these two, a minus omega 1, well, a times 1 minus omega 1 over omega 2 is equal to 1. Or a is equal to 1 over 1 minus omega 1 over omega 2, and then a is equal to omega 2 over omega 2 minus omega 1. Okay, so that's what a is. And b is just, I divide that by omega 2 and multiply by omega 1. So I'm going to get b is equal to minus omega 1 over omega 2 minus omega 1. Okay, so that means I found what the excuse me, what the solution is, right? So let's see what the solution looks like. Let's look at CB because that's, I think, more instructive, because CB is related to the occupancy or the excited state, right? So I have this CA, so what am I looking for? I have this as a function of time. This CB starts from 0 and CA is equal to 1 at time equal to 0. So this thing is going to change, okay? It's going to increase, and its magnitude squared is going to give me the probability of finding the particle in the excited state. Okay, to conserve probability, we are not making approximations here. CA must decrease. So the CA squared plus CB squared is going to be equal to 1. So let's see what CB is. So CB is going to be equal to, let me write this coefficient out in front, 1 over 2I h bar V A B e to the I omega minus omega 0 t. Okay, so I have this time dependence, but then I also have these terms. So A is, where is it? Omega 2. Okay, careful. There's omega 1 times A, so it's going to be omega 1 times omega 2. There's a common I, so let me pull that out. Okay, I'm just writing these terms. All right. And in the denominator, I have omega 2 minus omega 1. Then I have plus b times omega 2, so that makes it omega 1, omega 2, but it has a minus sign, so minus omega 1, omega 2 divided by omega 2 minus omega 1. Okay, I forgot the important factors, e to the I omega 1t minus e to the I omega 2t. All right, this will simplify quite a bit, as you can see. So let me write that out. So it's going to be I, all this stuff, 2I h bar v a b e to the I omega minus omega 0 t, okay? And then I have these terms, okay? Let me do it slowly. Omega 1, omega 2 minus omega 1, okay? And then e to the I omega 1t minus e to the I omega 2t. All right, so let's put in what these things are. I over 2I, well, the i's cancel, right? So pull that out. 1 over 2 h bar v a b e to the I omega minus omega 0 t.
1 over 2 IH bar should have been below for a while.
Which one?
2 IH bar. So it was on.
Oh, okay. Thank you. So over here, right? 1 over 2 I h bar. 1 over 2 I h bar, which means I can make this a minus 4 h bar, right? Okay, what is omega 1 times omega 2? So omega 1 and omega 2 are these things, right? So if I just multiply these things together, where do I do it?
Why do I have minus 1?
I squared. Okay.
I squared, yes, but why 4? We should have minus 2.
2, okay, thank you. Anything else? Okay. Let's calculate omega 1 times omega 2. So omega 1 times omega 2 is going to be, I have two terms, something plus something, and then something minus the same thing, okay? So if I multiply them together, I get the square of the first minus square of the second, right? So I'm going to get 1 over 4 omega minus omega 0 squared, right? Minus the second term, so that's minus 1 over 4, okay, square of this, so it's going to be omega minus omega 0 squared plus VAB magnitude squared over h bar squared. Okay, so that cancels that, and I am left with whatever, minus 1, okay, VAB magnitude squared over 4 h bar squared. All right. Omega 2 minus omega 1, okay, is the difference of these two things. Okay, difference of this from that. So I have to decide which one is omega 2 and which one is omega 1. Okay, so let's just decide on something. Let's take the, lower one. So let's call this thing omega 1, 2. Okay, so the upper sign is for omega 1. The lower sign is for omega 2. So omega 2 minus omega 1 is the lower one minus the upper one. So I get a minus, but that's okay. So omega 2 minus omega 1 is minus 2 omega r. Okay, so it's time to put all of those things in there. So the minus signs go away, and I'm left with VAB squared over 4h bar squared divided by 2 omega r, and I have e to the I omega 1t minus e to the I omega 2t. Okay, so that's what it looks like. So if I put t equal to 0, obviously I get 0. Okay, so at least the initial condition is correct. So now let's look at what the magnitude of CB is going to be. CB squared is going to be. So a bunch of terms. So here I have 4h bar squared divided by magnitude of VAB squared. Okay, I'm looking at magnitude squared. Magnitude squared of the exponential is just 1, so that doesn't contribute. So let me remove that. Okay, and then I have this thing now going to be VAB to the 4th power divided by 16h bar to the 4. And here I have 4 omega r squared. All right. Now the magnitude of this. So I have to multiply this by its complex conjugate. Okay? So it's e to the I omega 1t minus e to the I omega 2t multiplied by its complex conjugate, e to the minus I omega 1t minus e to the minus I omega 2t. Okay, so certain things will cancel. VAB squared, 2 factors will cancel there. And 4h bar squared will cancel, 4h bar squared there. So let me just squeeze one more line here while I can. So this is going to be equal to VAB magnitude squared divided by 4h bar squared. Okay, this guy. Then I have 1 over 4 omega r squared. Let's see what this is. Okay, there will be terms which multiplied together will give me 1. Okay, so I'll get a 1 for this term and also another 1, okay, minus and minus, so that's going to be 1 for that one. But then there will be cross terms. So minus e to the I omega 1 minus omega 2t minus e to the minus I, omega 1 minus omega 2t. Okay, it's complex conjugate. So it has to be real. Right? So this thing here is twice the cosine of omega 1 minus omega 2t. Okay, with a minus sign in front. All right. So we have to finish the calculation somehow. So this is our significant result. What is the probability of finding the particle in the excited state as a function of time? Okay, first of all, I have a term there which has the form 2 minus 2 cosine of something, okay, x. Something which looks like that. So that's 2, 1 minus cosine x. So what is that? Experts in trigonometry. 4 sine squared, right? Because it goes to 0, x over 2, right? So that's a sine squared term. All right, so let's put that in. So CB, okay, I hope you are checking my algebra. It's a miracle if we can get all the constants right, but the form seems to be okay. So it's VAB squared over 4 h bar squared. And then I have omega 1 minus omega 2. Okay, so let's see what we have here. Omega 1 minus omega 2, okay, we had it over here actually, is 2 omega r. So I'm going to put that in. Okay, so 1 over 4 omega r squared, and then I have 4 sine squared of omega 1 minus omega 2, which is 2 omega r, but then I also divide it by 2 t. Right? Is this okay? There's a minus sign, but it's squared, so that's good. Okay, so actually it's quite nice. I have something which looks like VAB squared over 4 h bar squared. Okay, so this is a factor which tells us the strength of the coupling between A and B. Okay, if this is 0, obviously CV just stays 0, right? That's just the interaction between the, okay, for the particle to go from A to B. And then the force cancel, that cancels, and I'm left with something which looks like sine squared omega RT divided by omega R squared. All right, so what does this look like? Okay, it's a sine squared. So it starts from, okay, so this is CB squared, which is really probability of finding the particle in state B, is going to be something like this. Okay, so it's going to oscillate. Okay, and the maximum, and this is equal to 1, is going to be proportional to this VAB squared over 4 h bar squared omega r squared. Okay, so it's going to oscillate, and its magnitude depends on the strength or the coupling, okay, or the two systems. And obviously, okay, so what we have found here is that this is oscillating like this, and this is going to oscillate in the opposite direction, so that when I add them up, I'm going to get 1. Okay, so the particle is either in A or B. Okay, so it's oscillating with this Rebai frequency. Okay, so this is called the by frequency. And has a form like this. Okay. So, any questions about this? Because now we are going to go ahead and solve the same problem using perturbation theory. Yes.
Does it mean the particle oscillates between two different states?
Yes. Okay. Well, the particle doesn't oscillate really between the particle state, but there's a probability that the particle will be in the higher energy state, which oscillates. Okay. So if you look at the system at any time, if you start with the particle in state A, at a later time you are going to get the particle, some probability that the particle is going to be in state B, but it will just oscillate. Now, you see we have sort of, if you look at all of these equations, it's actually quite symmetric. So if we were to actually look at a problem, okay, so alternatively, if we had CA at time equal to 0 is at 0 and CB at time equal to 0 equal to 1, it would be the opposite. Okay, so in that case, then we would get a CA, okay, which is going to oscillate like this, and a CB, which is going to do the opposite. Okay, whatever, I can throw it on ice, but you can get the idea. Okay, so you have something like this. So in some sense, this oscillatory perturbation is promoting the transition between these two states. Okay, if it's in B, it's trying to push the particle into state A. If the particle is in state A, then it is, okay, being put into state B, and it just oscillates. So what does that mean? If I have these two energy states, okay, EA and EB, so the particle can be in this state or that state. And if I am sending in a particle with some, if I'm just providing a perturbation with certain frequency, okay, that is promoting a transition from one state to the other. Now, you see, if you look at the magnitude of this is going to be maximal, okay, when this omega r is going to be small. So what is omega r? Omega r is this quantity here. So maybe I'll just copy it over here. So omega r, okay, is equal to omega minus omega 0 squared plus VAB squared over h bar squared. Okay, and that's that. So you see, if you want this transition probability to be as much as possible, you want to make this omega r as small as possible, which means you should choose your driving frequency, omega. Remember what this big omega is. This is the external, okay? This is the perturbation frequency, okay? Whereas this omega 0 is related to EB minus EA over h bar, right? So if the perturbation frequency capital omega is equal to the frequency associated with the energy difference that will cause the largest amount of transition, okay, and enhance the transition at a maximum. So I have an energy difference here which is equal to h bar omega 0. And if my h bar omega, capital omega, is equal to that h bar omega 0, I get a maximum amount of, okay, transition from state A to state B. So what is happening here? The field which is causing this oscillation, and remember we discussed that as some sort of electric field coupling to a charge type of model. So in that case, the energy in the electromagnetic field is going to help to excite this particle to the higher energy state. Okay, so, and that happens at most when the frequency here is the same as the frequency associated with the energy difference. But not only that, if the particle is in the excited state, this effect, okay, this perturbation is also promoting the transition of this particle to the lower energy state, okay? So this event, okay, going up is associated with absorption, okay? So it's absorption of energy from the field, okay? So that you put the particle in the higher energy state, okay? And this process going down is associated with emission. Now it turns out that electromagnetic waves have this property that the energy come in quanta, okay, in photons, which you have seen. So what happens is that the particle either absorbs one quanta of photon and it goes up to the higher energy state, or it emits a photon and goes to the lower energy state. Now, because this electromagnetic energy is related to this emission processes, these are called, okay, stimulated processes. These are stimulated by the field. So this is stimulated emission. You have one photon that comes in, and there's already an excited atom here, and it causes the emission of a photon. So one photon comes in, two photons go out, okay? Or the particle is in the lower energy state, and then you just send in a photon, and the photon is absorbed. So it's a stimulated absorption. The photon goes away, but the particle is in the higher energy state. Okay, so what you can do is you can use this to construct all this laser technology. If you have lots of atoms and you can prepare them all in the higher energy state like this, okay, so you have lots of atoms, okay, all of them in the higher energy state. You send in one photon, okay, at the proper frequency. Now you have two photons flying here, and that will cause an emission here, and now you have three photons going there, and so on. Okay, so since these are nice, well-defined energy levels, all the photons will have the same frequency, same energy, okay, and will be moving through the system. So obviously, previously you have to prepare your system in this form, okay? So you have to prepare your system so that all these particles are in the higher energy state. And that, of course, you can do by various means. You can just, okay, flash a large amount of electromagnetic energy with all kinds of frequencies, so those that match will excite these things up etc. So that's called pumping the laser. So you pump the laser so that it is prepared in the higher energy state, and then okay, you get also emission. Now, besides these, there is also a, okay, so versus spontaneous, okay, emission. You cannot have spontaneous absorption. Okay, spontaneous emission is when you have the particle in the high energy state, it's just sitting there, and even if there is no electromagnetic field, okay, so you have killed all electromagnetic fields, put your system in a very cold place, okay, so that there are no thermal fluctuations, etc. Still, okay, every once in a while, this will, okay, fall into the lower energy state and emit a photon. That's called spontaneous emission. Okay, so why does it do that? Well, you can relate this to the, okay, the 0 point, the ground state energy of the oscillator, the electromagnetic field oscillator, okay, which acts like a harmonic oscillator. So even in its ground state, it will, okay, just stay there. Yes?
Is energy conserved in this system?
In which system?
This kind of...
This whole system? Yes. Yes, okay, so you see, we are not writing the dynamics of the electromagnetic field here. Okay, so the energy is absorbed from the electric field, so you have one less photon in the electromagnetic field, but we are not doing that part of the calculation. We are just looking at what is happening to the electron when it goes from one state to the other. So from the perspective of the electron, no, the energy is not conserved. Okay, it goes from lower energy to higher energy. But if you try to solve the problem together, electromagnetic field plus the electron, okay, then that is a nice problem in photonics, for example, if you take a course on photonics, because then you very nicely quantize the electromagnetic field also, okay? So then you have the electromagnetic field dynamics of the electromagnetic field as well as the electron being tracked. There you can quite, okay, simply see that the whole energy is conserved. Okay. Okay, maybe we'll give a break and then go on.